Hello, this is video 3 for Module 8, covering some of our new, more complex reactions, generally speaking. So this is the end of the quarter, basically, the final push. We're putting together everything, all the knowledge we've learned from structure and bonding, stereochemistry, electron arrow pushing, putting it all together and touching on the science of synthetic organic chemistry, which is mainly the topic of Organic 2 and 3, reaction chemistry. So the next reaction is bromination of alkenes. This one's not too bad as far as complexity. The interesting aspect of this is that bromine can act as an electrophile, something that draws in electrons from an alkene, which has electrons to give. And the arrow pushing for this is legitimate. Electrons from the alkene would bond to one of the bromines. And why, if this is a symmetric molecule, bromine, why would that happen? The key is in the way that electrons can sort of slosh around. So on a very small time scale, electron density can appear like this, even in a symmetric molecule like bromine. So notice you have higher electron density sort of sloshed to one side momentarily. Well, that momentary movement of electrons can create what we call an induced dipole. And then once that induced dipole forms, it can go ahead and induce dipoles in more bromine molecules around it. So in a way, you could look at the electron arrow pushing down here as delta plus, delta minus, driven by inductive effects. Formation of a bond, breaking of a bond, leads to this intermediate that we call a bromonium ion. So charged intermediates, which are ions, have the suffix onium ion sort of tacked on, like hydronium ion, we already seen. The second bromine can come in, as you see the arrows here and here, with bond forming and bond breaking of this three-membered ring. Notice these electrons of this bond are going toward a full plus charge. Notice the bromine that was bonded initially stays on the top face of the molecule, while the bromine coming in comes in from underneath. That makes sense if you really look at the bromonium ion intermediate. This bromine here is always going to be cis or syn bonded to the two carbons. It's difficult to get a three-membered ring trans if you think about it. So you get anti-addition in bromination or halogenation. And because you can have two different bromonium ions, you can have two different products forming here. So keep stereochemistry in mind. And you're going to introduce a lot of RS stereochemistry in these reactions. Okay, moving on. I want to remind everyone of the issues that we covered in the previous videos with getting mixtures of products from different carbocations forming, and then from the different kinds of arrangements that can occur. So in a reaction like this, you end up with three possible products, the third being from a hydrogen migration. And organic synthetic chemists have dealt with this by coming up with new reactions that correct this issue of multiple products, many multiple products. So we call that regioselective synthesis. Only getting the products you want, the atoms adding to the atoms that you want them to add to, and so forth. So inevitably, to get these to be effective, we delve into more and more complex reactions, however. So the old, just simply adding acids or alcohols or halogens or this kind of stuff will never get you the selectivity of the more complex reagents that we see. The two complex reactions we're looking at here are oxymercuration, demercuration, and hydroboration, oxidation. If you start with an alkene like this, these two reactions will lead you to one or the other specific products. The alcohol adding to the more substituted carbon, the carbon that was more substituted initially, or the alcohol adding to the less substituted carbon in hydroboration, oxidation. Notice the net addition of these reactions is the addition of water. So in that sense, it's not different from some of the ones we've seen before. So this is important to remember and to recognize these reaction conditions. So if you see these reaction conditions, you will get either product specifically and only that product. The key feature that gives these reactions this kind of specificity is that no carbocations are formed anywhere during the process. And we've seen already, the formation of carbocations is problematic in various ways. So by avoiding the carbocation formation, specificity is achieved. But you won't understand this until you look at the detailed mechanisms. We'll go into the detailed mechanism of oxymercuration, demercuration. This has its origin in the fact that metals in their normal sort of metal state are electron donors. So if you mix mercury with acetate units like you see here, and these will form bonds in which the mercury sort of is more of the electron donor in the bond. So this species that's formed is mercury with two acetate groups, some abbreviated like that, AC group. This is your AC group. This is the reagent that will be used in this reaction, along with another one in a second step, which is the demercuration step, a reductive step. So there's an oxidative step with mercury, and then a reductive step. And here again is the net reaction. Assuming this is the more substituted carbon to begin with, the OH will add to that carbon exclusively. So how does this go about? Here's a specific example where one of the carbons, notice, is more substituted, has a methyl group on there. Here's our mercury reagent. This is the oxymercuration step. Arrow pushing is relevant here. It forms another onium ion, the mercuronium ion, shown here. Same deal where there's a plus charge basically on the mercury. Three-membered ring, syn or cis in geometry. With the addition of water, you have bond forming, bond breaking. And you get to this stage here where the alcohol then from the water, right, has added and deprotonated in that second sort of trivial step of deprotonation. The mercury is still attached here with this bond that was there and is still there. The second step is simply to remove the mercury, and that's using this hydride reagent. We would call it a hydride reagent, sodium borohydride. When you see a hydride reagent like this, you can consider it to basically be the equivalent of a hydride, which is H-, and can't really exist on its own floating around in solution, but it's delivered from the sodium borohydride molecule, as we'll see in a moment. So the arrow pushing for this is effectively an H- nucleophile displacing the mercury reagent, leading to this new bond, as we see here. And the final alcohol product, the net addition of water, notice the alkene is gone, and exclusively we get the OH adding to what was the more substituted carbon. So a digression on hydride reagents is relevant. Boron and aluminum, if you look at the periodic table, are in column 3, which in formal charge counting would give us a +3 to begin with. A molecule like BH3 is +3 for boron, -3, 1, 2, 3 in formal charge counting, 0 formal charge. But notice BH3 is still short an octet. So it's an unusual case where it's neutral but short an octet. Because it's short an octet, it's a Lewis acid or an electron pair acceptor. So you can create ionic compounds with BH3 or ALH3, aluminum, and by looking at these, so these are the hydride delivery reagents. You can form these ionic salt-like molecules. The delivery of the hydride comes from any one of these hydrogens on the boron in the same way that you see on the left. And same with aluminum hydride. So we have sodium borohydride, and aluminum borohydride. Lithium aluminum borohydride. So in the oxymercuration, demercuration, in the demercuration step, we use sodium borohydride simply to add or deliver the equivalent of a H- ion. The key feature of the oxymercuration, demercuration, that makes it so precise in where the OH adds is the mercuronium ion itself. So in our earlier example of this molecule giving us problems, I think it was a similar example, the mercuronium ion formed is here. If you look at this mercuronium ion on the right, redrawn, showing the atom sizes, the size of this mercury atom here causes this bond right here, to stretch on the side where there's a larger carbon substituent. The more substituted carbon, right, is right there in the structure. Because of the size of the mercury atom and the steric effects of the larger carbon group on this side, it makes this bond stretch, and so this bond is now longer and weaker because of the stretching. That's what enables the water coming in to bond to that carbon. It's the driving force of the breaking of that longer, weaker bond. It's the energetics that are affected by these steric effects. So the steric effects lead to energetic control. So it's interesting that one feature is what controls where the OH ends up from the water initially. And it's a very specific reaction in the high 90 percentiles. For the detailed mechanism of hydroboration oxidation, I'm going to refer you mainly to the reading, but I'll point out again the same sort of key feature in that process, which is that the boron reagent reacts with the alkene in this way, so simultaneously forming these two bonds here and here. And it does that in triplicate, interestingly. So in the end, you get a trialkyl borane like shown here. The carbons 1 and 2 labeled here on the left are relabeled here. And so this would be 1 and 2 again, 1 and 2 again. So they're all the same, where the hydrogen initially adds to carbon 2, the more substituted carbon, and the boron, notice, is attached in each case to the less substituted carbon. Upon oxidative addition, you end up then with the alcohol attached to the less substituted carbon. So it gives you that alternate to the oxymercuration, demercuration. The same net addition of water, addition of the alcohol to the less substituted carbon. And that's controlled and set up, not by a mercuronium type ion, but through this trialkyl borane. So a very different approach, giving you the same level of specificity. And that's the end of video 3, module 8.